Alright, should be making a video. Yep. Alright, comment video. Oh my god. It's a long comment. Okay, so the acorn. I really like your idea regarding magnetism being a filter of gravity. Yes, it makes sense that it's a filter because it doesn't burn any energy. I think it is a great explanation. One question, however, does the strength of the magnet decrease in relatively low gravity? Obviously, any gravity it's in is going to affect the magnet the normal way. Again, you have to understand the magnet is merely going to interpret the field that's around it. So it isn't affected by what it expels. And so it's just going to convert whatever there is. So it's always going to look the same. So if, like say if you're in less gravity, then obviously it takes less magnetism to lift something. So it would always be relative to the gravity potential. It will, yes, so the simple answer to the question is, yeah, it would be relative to the gravity field you're in. I mean, I hate to even say yes, just because I probably should think about that some more. Like, what if you're right between two gravity fields? You're still being exposed to gravity, so that's the point. So, to have substantially less gravity, that is force hitting you, that doesn't really happen. You just change which way the force is going through you, right? From the outside in. So the question would be, well, I don't know if I want to get into the complexity of it. The simple answer is it won't change anything because there's no such place as some place that's under low pressure in reality. It's just a change in the pressure in the sense that you have more on one side than you have on the other, or you have more black than you have red. And the black-red thing affects the atoms regardless. So the gravity effect on something is based on the fact that it has protons and electrons. The magnetic effect is based on the fact that the protons and the electrons are in an arrangement. So you can't change the gravity, but the magnet's always going to convert whatever gravity exists. The gravity, again, see this argument about what gravity exists, right? Like I said, if I'm in between the moon and the earth and I have zero gravity because I'm being pulled equally, it doesn't mean that I'm in no gravity. To get my point. Alright. Such as free space beyond orbital zones of planets and stars. Well, like I said, the free space is the most pressurized. So that's the most gravitational in the sense. You have you're getting hit by the raw force, unfiltered, unshadowed. All you can do is shadow the force. You can't make the force stronger. So in naked space, the force is the strongest, and it's only when you get into where you're being shadowed that the force can be decreased. But obviously it doesn't get decreased because as soon as you're in proximity to some other material body, right, then you start being affected by the fact that other things, once you're on, like, say, the surface of the earth, right, the stuff beneath my feet may not be being affected by gravity as much as it's being affected by my feet pushing down on it, technically. So the pressure is hard to evade. Okay, well, anyway, according to most explanations, it would not, and does not in reality, since the ISS and many satellites contain magnets while being in a much weaker gravitational pull by the R-squared law. So again, you're not getting what gravitational pull means. It doesn't mean less gravity. It just means that there's more pressure on one side than there is the other side. And if you're feeling less gravity, that means the pressure is equalized. So you're in essence under more gravity. There's more force moving through you. The further away you go from the earth, technically, you're getting hit by more force, not less force. It's just you've gotten rid of the low pressure part. So your argument would have to be more like what happens when you're in the center of the Earth, or you could make some hollow sphere and create zero gravity inside the hollow sphere. What would happen to a magnet, let's say? That's the more interesting question. While being in a much weaker gravitational pull. So again, it's not the pull of gravity, it's the presence of it. So the lights are always on in the universe. You have to think of the universe as the opposite way. The black space is full of energy. The light spaces are full of pressure, going in. So I'm just saying, so you're just making a simple mistake where you're just thinking about it the wrong way. The less shadowed you are, the more force you're in. I don't think you would say it would either, but this is why I'm asking to clarify. I'd imagine if your model, the strength of the gravitational field does not affect the magnet unless it is an incredibly strong gravitational field. No, it would have to be the absence of the gravity. That is, you're blocking it, a lot of it. So, from one side. And then you could logically argue that the magnet would have less pull from that side, but it wouldn't need the pull because the gravity would be so strong pushing in the direction that it has less pull. So I'm just saying that it's always going to compensate in some way or another. Not always, but I'm just saying, I can't make any statements about the impossible thing, right? So even the idea of making a hollow sphere, you have to understand that the only way you could do that is you'd have to have the inside of the sphere would have to be made of something that could withstand the crushing pressure. So it would have to be some insanely strong material that could not collapse, that wouldn't collapse under the huge weight that's on top of it. So the only, so it's, in a theory, you can't even test it because you couldn't make the very thick hollow sphere to test what the real absence of gravity is like. The absence of pressure. And then in theory, what would happen to your magnet if it was in such a low pressure is it might just fly apart, just like I think water would evaporate in space because there's no pressure, so its boiling point would be like 3 degrees or something, without pressure. And so the point is if you put some matter inside the hollow sphere, it probably would just explode because of all its internal pressure, and there's no external pressure compressing it anymore. I mean, these are decent enough thought experiments, but fine. I mean, I don't think there's anything in here that says we have evidence that this doesn't work. So, like I said, so it does. It's not going to affect the changes, the small changes, and frankly they're small, between surface gravity and empty space gravity wouldn't be enough for you to detect it in a magnet. I'm just trying to think if there's any test you could do, but I can't think of anything off the top of my head. So anyway, the magnet only requires a presence of a gravitational field. And just understand that the gravitational field exists in empty space the strongest. So it would work in almost every area of the universe, since you would be hard-pressed to find space devoid of at least some gravity. Well, again, the empty space has the most gravity, and the tricky part is if you find a place that has low gravity, it's likely to be a place that has high pressure from the chemical atoms. So in a sense, the gravity is there. It's just more personal in the sense that you're going to get it because the electrons have been affected by gravity, and they're going to push into your electrons and create a horrible amount of pressure. So you have to go somewhere where there's a huge amount of chemical pressure or atomic pressure to escape gravity. All right, another question. What do you think the width of a photon is in the visible light spectrum in your model? I don't think it's relevant. It can be, just go ahead, pick any number. Its momentum is the only thing that matters, and the fact that it hits electrons. So but I don't think it needs to have a width, a photon. It's a force, and the width of the electron would be the more interesting question. I've heard you compare it to things that are incredibly small, as in smaller than atoms and electrons. Well, I don't know, if you don't already know that photons are a lot smaller than atoms and electrons, then you're way behind. I mean, they clearly hit electrons. They clearly vibrate them. However you want to think about that, is ether or anything. It doesn't matter what your premise is. I mean, that's already kind of known physics. Photons hit electrons. After doing further research, it appears that the wavelength variable in C wavelength times frequency. Well, again, why would you even do wavelength times frequency, right? They're just inverted numbers. They're going to give you 0. Isn't the width of a photon, as I stated in the previous comment? Well, I don't remember that, but whatever. But a photon probably / intensity variable. Again, I don't know. See, it is curious that people think about things that just, I don't know why they bother wasting time on them. I would argue that photons are fairly competent at moving electrons. So their momentum has to be something like 10 to 1 or 100 to 1. I don't think it could be 1,000,000,000 to 1, right? Yeah, I don't think so. And light is such a weak force when you look at it compared to gravity. As I've stated, I mean, to move this object just a few inches with light, you know, you need a huge amount of watts to do that. Where this, falling by gravity, it does it, you know, it happens right in front of you. And we don't think about the huge amount of energy it would take if we had to actually do that, move something. But anyway, so gravity's hugely dense. And photons are a tiny percentage of the energy in the universe, visible photons. Yet they have a pretty remarkably strong effect on electrons. So you could argue that that's because of this wavelength thing, this resonance frequency, the fact that you have to hit electrons to move them out of their pressure. You have to hit them at a certain speed, and if you hit them slow, the energy is going to be destructive, and so you have to do it on a resonant frequency. So you keep moving them in one direction, so they can release a new photon of the same intensity. So let's see. So yeah. So, but the size of the photon, like I said, what would it matter? As long as you understand it has a momentum, then what's the difference? What size it is? I just don't know. It's the smallest thing in the universe, so who cares? There's no evidence that there's anything else manipulating anything, so why worry about what size it is? You won't hear the wave community admit this very often, though. Yeah, well, I don't know why like I said, I'm not too sure your equation makes any sense anyway. C, the speed of light equals the wavelength times the frequency, just doesn't make any sense to me. The wavelength is a 1 over, and the frequency is a blank over 1. So, I mean, they're two different numbers. I mean, they're inverses of each other. You won't hear the wave community, but okay, they'll simply say that the photon is a wave, rather than understanding that sinusoidal curves are simple and common in terms of patterns and structures in nature. Well, again, there's no. I think there can be the argument can be made that it has nothing to do with a sinusoidal anything anyway. The fact is, the photons are received as digital information, essentially, as quanta. So again, that's supposed to be the point made clear in the ultraviolet catastrophe and in Einstein's photoelectric effect, is that it doesn't matter what this sinusoidal bullshit. All that really counts is that there's a clump of energy of a specific amount. They are especially quite common when you start modeling geometric patterns and shapes with mass. Again, you can convert anything into anything. In a sense, you can convert digital information into sinusoidal analog information. I just don't know if that's really being accurate. With this information, one could replace the wavelength variable with a more apt and descriptive word such as intensity. Yeah, I think that would just get you into more trouble, because I think that's the wrong way to look at it. Its frequency is a fine word. If I shoot bullets at a specific frequency, that's understandable. Cannonballs at a specific timed frequency, that's understandable. Even the word wavelength, but you just don't combine the two because they're the same thing. Period. Period, wavelength, frequency. It's all the same thing. You're just talking about a time cycle. How else to say it? But the intensity, again, like I said, if I shoot cannonballs one a second, and then I shoot cannonballs every half second, I have twice as many in one stream that I have in the other in an amount of time. So clearly one's going to seem more intense. But again, part of how we're measuring intensity is based on what does an electron do. And what the electron does has to do with it being on resonance. So the electron, it reacts to certain wavelengths more than it reacts to other wavelengths. And that's sort of given people an illusion of strength that I think is just an illusion. But clearly, ultraviolet light, it's quite possible for it to contain more energy because they're closer together in the same amount of time. But again, we're back to ray length. How long is the ray of the force? So with light, the rays are emitted by atoms, I would argue, by individual atoms shoot little rays of light. Where in stuff like radar, all the atoms are emitting on the same time cycle. So the rays they're still rays, but they can be any length. They can be very, very long. They can be constant. Where light is always going to be broken into a bunch of rays. Let's see, of specific length. Let's see, so where were we? Well, I'll just read this last paragraph again, I guess. With this information, one could replace wavelength variable, as intensity. Thus, we have a standard pattern or frequency that the packets of quanta come at. Yes, rounds per minute, as you've compared metaphorically before. Yes. And an intensity grouping of differences, as if you added an extra gun barrel or two for some of the rounds. Yeah, well, again, this intensity word is just a little dangerous, is all I'm arguing, because it really does have to do with, it's like our own eyeball. If you're saying that we can only receive, let's say we could agree that we can only receive light that has, say, 6 nodes, right? 6 cannonballs or 6 nodes in the wave. So that's a certain size or hunk. And if you cut it in half and it hits our eye, we don't see it. It's not counted as a photon. Now, it's still energy. It's still going to affect things, but it's not going to affect them in the same way that's going to create an electric current. So that's the difference. So there's a certain mechanism that creates the effect that we can see. We can't see the electron just doing this. It has to do a specific kind of that, for us to see the effect. So every movement an electron does isn't something we can detect. We can only detect certain kinds of movement. Alright, intensity. Grouping different, as if you add an extra gun barrel to some of the rounds for each element of that pattern frequency. Thanks for the time. No problem. Yeah, so it's just a little bit complicated, and obviously a lot of people just don't want to bother with the complications. But again, it's like this whole electromagnetic spectrum. The force is created in subtle different ways at each frequency. Well, there's like 2 ways. Certainly antennas are different than burning a filament. Those 2 ways of creating photons are different. Alright, magnet has force, not energy. I would argue that's a kind of useless distinction. So it depends on, as I've stated before, the word energy sort of gets broken because the only things we count as energy are imbalances. So we count the energy of the water falling from the sky, or the river flowing down the mountain, and we say there's energy, right? Because we see it. But we don't look at a cloud and say there's energy, because it's not doing anything. It's just sitting there quietly, staying where it is. So the problem with the word energy is that it just doesn't cover it. It just doesn't say it well enough. And then you get into the idea of, okay, potential and kinetic. So at least you have two forms of it. Well, again, the potential energy is everywhere. I mean, every single physical object has, nuclear explosion. I mean, the atoms in this stupid lighter is enough atoms, enough pressure, enough energy is trapped in here to blow the world up. Just a fact. So if you could, create it, make the atoms unstable enough to release all of their energy, or not even all of it, to do some bisecting of the atoms, breaking of the nucleuses. If I could break the nucleuses, split the nucleuses in half, I'd gain enough energy out of this stupid lighter to blow the world up. So clearly the word energy is kind of messy. But also clearly the word force, you can't have a force that doesn't have energy. It just doesn't make any sense. So this is just semantics. All forces are electrostatic force in nature. Well, says you by declaration, Joe. I mean, it doesn't say anything. I mean, clearly, as I'm pointing out, the only way you can have a force is to have something that's going to reflect, okay, to create more pressure, or that's going to mitigate a force, that is to divert it, to have less pressure. So the only way you can have a force is to affect an electron or a proton. They're the matter bits, they're the things that are getting manipulated by the force. Without charge, the force can't do anything. So, yeah, clearly it's all electrostatic if you want to recognize that the two relevant matter bits are electrons and protons. They're the ones that are manipulated by the force, and everything else is a composite. So yeah, pretty much nothing statement, thank you. I mean, one sentence. I'm going to do physics in one sentence. I mean, yeah, that's not going to work. So another big comment. Okay, but at least these much better to have where you get to a point. I mean, I'd rather have a conversation with somebody, then you can do this back and forth thing a lot better. So anybody willing to argue the standard model, or anyway, any of the standard notions, bent space, virtual photons, dark energy, black matter, all that crap. I have a problem. A microwave photon, a radio photons, cannot pass through the door of a microwave oven door. Yes, the door of the door. That's what the mesh is for, to block microwave photons. Well, see, the idea of blocking just means converting, in my opinion. So what those holes are actually doing is it's letting a ton of energy through, but it's broken the rays. So now the microwaves are in smaller pieces, because they're not perfectly aligned, so they don't get through the holes. So part of the energy hits the door and part of the energy doesn't. So the ray that was this long ends up being converted into one little pieces, because some of the ray, it has one of the cannonballs is here, one of the cannonballs is down here, another one's here, another one's here, another one's here, right? So when that ray heads for the hole, yeah, some of the bits get through, but some of them don't. So now the frequency and the length of the ray has been broken, right? So, I mean, I could draw it, but I think you can get it. Right, so if there was cannonball, 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 right? At a frequency, standard frequency. Now, it's just cannonball, cannonball, cannonball. So there's the right frequency here, but the wrong frequency here, and then another wrong frequency there. And so the continuity of the frequency has been broken, as well as probably the length of the ray. So in two ways, the light has been degraded into basically gravity. So gravity comes out the door, because the standard frequency needed to make a photon has been destroyed. All right. Microwave photons, but only certain frequencies can pass through the mesh. Well, it's not really a mesh, just a bunch of holes. But yes, and it's not about certain frequencies passing. It's I touched the microphone. It's about the polarization. So as you go lower in frequency, polarization gets bigger. Okay, and that means the fact is that as the frequency gets longer, you can sort of understand that whatever's emitting the frequency is moving in the atoms. The atoms are moving, they're going around the Earth, they're jiggling, they're doing all kinds of moving. So the slower the frequency that's coming out of an atom, the more likely the electrons and protons have moved their position as they're shooting the cannonballs. So that's how the cannonballs get a little bit out of alignment, is the cannon moves more when the frequency is slower. There's more movement in the cannon, where if the frequency is fast, the cannon can't move as much, and so the polarization is less dramatic. So there's an association between the width of polarization and the length of the wavelength. The polarization is more extreme the more you increase the wavelength. All right, microwave photons. Okay, I asked a physics forum that if a photon is a point particle, like physicists say, then how can a microwave door block it? So again, the physicists don't say it's a point particle. They say look, they don't really say anything rational, right? But clearly, when they draw this stupid wave thing and this way, they're clearly identifying something that might have a ray length. They don't ever talk about it, but they're clearly talking about something that has a ray length and that it has nodes. So you can say that they say it's a point particle, but what they're really saying is that the nodes, if we can get away with saying the nodes are the real photon or whatever, or the antinodes are the photon, they're really saying is that thing doesn't have any known dimensions, but it's only because we can't see it. And I would argue it still doesn't matter. Mathematically, they like to turn everything into having no volume, because their math works better that way. I don't know exactly why it would, but I think it just has to do with the fact that it just makes it easier, let's say. And any differences would be so small that we could never detect them anyway. So whether they made it this big or this big, it's not going to make any difference to most mathematical equations. All right. And the answer I got was that the photon is not a point particle but a quantum field excitation. Well, clearly they think it's a field thing. You know, it's made up of some sort of whatever field is. It's made up of field, electric field and magnetic field. Obviously, I would argue that's just empty rhetoric. They have no description for this field. It's a fundamental function. It's a fundamental player in their physics, and yet they give us nothing. So they might as well just say it's spent space. That take on different sizes. In other words, not a particle. Well, obviously, if you think conventional physics, whenever they use the word particle, that they believe in particles, they don't. So there's just no point. And clearly, we can argue semantics. I mean, I can show you a bowling ball and says, look, it's a particle. Well, we already know that no, it's mostly empty space. So again, you know, this word falls apart. I'm arguing that the only things that are particles are electrons and protons, and that everything else is made up of them when it comes to matter. And the force is just made out of whatever you want to call the quanta that makes a photon, the quanta that photons are made out of. And photon is just a word for a ray of cannonballs. But the cannonballs, you could argue, are particles. It doesn't matter to me whether you call it that or not, but to me that's what they are. They're clearly a point in space that carries momentum. When that point in space hits you, it has momentum and it transfers it to you. All right. In other words, not a particle. I doubt the photon is a particle at this point. I doubt the photon is a particle at this point when it usually screams like a wave or a field excitation. Well, you can do whatever you want. I'm just saying there's the particle idea, there's no evidence that makes it not viable. So I'm just going to argue to you that I can explain to you why particles always work. And I think I've done that. The number of photons is not conserved. Well, I would argue that certainly it is, but quite obviously you're not going to be able to detect it. If I could take a laser beam and convert into gravity, as I'm just pointing out, a regular laser pointer. A laser pointer can't move hardly anything physically, can't move anything, can't even wobble a piece of paper perceptibly. So you have to understand that that little extra amount of gravity affecting something would be so minuscule that you wouldn't be able to detect it at gravity. So if I convert all the energy of a laser beam into gravity, it's not going to have much of a gravitational effect, is it? No, because its power is so much smaller, in terms of what we know gravity is capable of. So gravity is a much, they say it's a weak force, but no, gravity is the strong force because of its mere density, the amount of it. It's a preposterously thick force. All right, the number of photons is not conserved. Well, that's just, in my opinion, to argue that there's any evidence of a lack of conservation, I would say is nonsense. So all you can do is turn the photons to another kind of photon, like infrared heat, or you can convert them into gravity, which is motion. So the momentum is still going to show up somewhere. All we're really talking about is momentum. They can be created and destroyed. No, they can't. Like a wave in a pond can. Well, terrible analogy, so I don't know what to tell you. The finger has to have energy to poke a wave into the pond. I don't know where you get this idea that you can have a spontaneous eruption in your ether. Look up second harmonic generation. No, I'm not going to bother with that. That just sounds like absolute rubbish. Where waveguides are used to merge two lower energy photons. So you really think that happens somewhere? I mean, you could tell me to look up LIGO, right? And it's all based on what they say the experiment's doing. I don't get to sit there and inspect what they're doing. They don't have all their data open source. They don't show me exactly what the input signal was and how they, what they manipulated it through. So, what you're going to tell me that somebody says that they can do this thing? They use waveguides. Somehow they guided a photon. That's just absolute rubbish. Are used to merge two lower energy photons into one double frequency photon. Well, I mean, doubling the frequency just means you take two infrareds, you throw them into an electron, and you get an ultraviolet out. I mean, that's just a simple function of scatter. You can do that without any complex experimental crap. Converting is pretty easy. You can put heat into an atom and you can get ultraviolet out. You can put heat into an atom and you can get X-rays out. So what's magic? What's violating conservation? You put 4 cannonballs in as an infrared photon, and then you get 4 cannonballs out as 2 ultraviolets or something. How have or one the other way around? Two infrared photons with a total of 4 cannonballs, and you get 1 ultraviolet with a total of 4 cannonballs closer together. Where's the conservation violation? Oh, that's right, it doesn't exist. Okay, double frequency. A particle cannot do this. Well, I guess of course you can combine. I can shoot cannonballs 1 per second from one cannon, just do the same exact thing from another cannon, a half phase off, and have the two cannonballs merge in a location and impact something, and they'll impact it as if they were an ultraviolet photon. The frequency will be halved. So I shoot two cannonballs with this frequency, from two cannons, and I just have them intersect at a point where the effect can be felt as half frequency cannonballs. So again, there's no evidence that doesn't happen in reality. I would argue the radar experiment for the two-slit experiment is proof of it happening, because that's exactly what jamming is. Jamming is merely combining two frequencies, and you overlap them out of phase, and it's a new frequency that has to be looked for to be seen. Get it? Well, you probably don't, because I've already done that. Alright, a particle cannot do this. A wave has no issue with this. Well, again, a wave has lots of issues with wave spread, so you're using the word wave when you don't really mean a wave. You mean some kind of weird straight line perturbating thing. And all it is a frequency. Again, you can argue that your frequency of quanta is somehow not analogizable to cannonballs at a distance, but that's exactly what your nodes of your waves are exactly analogizable to. There's nothing about this crap that means anything, okay, except on, off, on, off. That's all it means. That's all the wave is sending, is an on-off signal. Cannonball, no cannonball. Cannonball, no cannonball. Completely analogous, so I don't see your argument is poo. Feynman struggled to eliminate fields and waves. Feynman didn't care about a mechanical understanding. He just cared about mathematics. And that's why in the end of his career he started going in all kinds of loopy directions where you borrow from the vacuum, where one electron can mathematically be represented as every electron in the entire universe, because we can just make the electron time travel and therefore be in every location at the same time. I mean, just ludicrous crap that was mathematically possible but has no relevance to reality. In his undergraduate studies, he constructed theories that use only particles, as he was a particle fan. Yes, he was clearly a clump fan, okay? Whether you want to call it particle or not doesn't really matter, but he's clearly, well after he was doing undergraduate work, clearly he saw these photons especially as clumps of momentum. But he failed. He admitted he lost confidence in particles in a book I've read by a guy that interviewed Feynman, The Lightness of Being, and fields have an existence of their own. Well, again, he fell into just purely saying it's random and it's mathematics, and he just didn't give a shit about understanding it as a physical model. He gave up on physically modeling reality. That made him upset. He may have said the photon is a corpuscle. No, he didn't just say it. He said it overtly. It's not a wave. He said it clearly. At one point, anyway, in his career, he was quite, in 1980, whatever, he was quite confident, okay? Confident enough to say, I wish they wouldn't teach people it's a wave. But in his book that the lecture was transcribed into, he called it a particle wave, and he bounced back and forth between wave and particle. Well, what he didn't do was glorify Huygens as an idea. He didn't think it was interference. He thought it was the randomness had a different source. I can't figure that one out. Well, I don't know why you're bothering with all this detail. Feynman's not the only source of understanding in the universe, other than he was perhaps talking like he wished it was a particle. No, he knew it was a clump. So again, I don't think he ever backed away from what quantum electrodynamics is supposed to be. I mean, clearly the word quantum doesn't mean anything if you don't clump it. All right, I mean, that was his point. Waves aren't clumps. Waves spread. waves lose energy. Waves have to affect things in directions in which they're not going. Wave is a silly word to use. Maybe he should have made it just that clear. If you want to call it something new. Because it's not a wave. It has no characteristic like anything we know of as a wave. It's not traveling through any kind of medium, and it's not perturbating things in all kinds of directions. Alright, it is down. I mean, it's a photon. It leaves one location and lands in another location, and you can always trace it to a straight fucking line. For fuck's sake. It is down to just a few dissidents that argue for it. Well, it doesn't matter. The facts still point out that if you reverse engineer any experiment, you'll find that the photons travel. You can perfectly explain how they got somewhere with straight lines. So you can pretend that there's some other truth, but no, that's the truth. But I gave up on particle concept. Well, that's your problem. Even though it was extremely stubborn about it for years. I don't know, he says I gave up. Why don't you say you gave up? Even though I was extremely stubborn about it for years. Well, again, that's your liability. I'm just saying wave is a silly baby explanation. It doesn't make any rational sense. There's no example of any such wave in the universe. Certainly not one waving in two fucking fields that don't even exist, that create, and those waves have absolutely no consequence because you'll never detect a photon just flying by your nose. It'll never happen. You'll never detect a photon because it brushed against an electron. No, it either hits something or it doesn't hit something, period. And you can pretend all this other crap, but it's just bullshit. So I don't know why you've decided to just wimp out and say, oh yeah, wave makes sense, when it can't make any sense, in my opinion, to anybody logical. Because waves don't do anything like what photons do. It doesn't make any sense. A torpedo is what photons do. They're like torpedo waves. So go ahead and show me a wave that looks like a torpedo. But the problem with it is enough to throw in the towel. Well, whatever. That's your problem. Name a single physicist in the establishment today that talks of light in particle terms. Well, again, there hasn't been any, and there aren't any. Yes, Feynman was the last, and Einstein before him, and the rest of them are all sissies, frankly. It's sissy physics. They're all spooky action at a distance with fake forces and fake fields and virtual this and fake that. So you want to believe that crap? Go ahead. I don't know. What can I tell you? It never made any sense to me. It's the point where I first said physicists are idiots, okay, in grammar school. Physics this has got to be a bullshit subject. This is like all the other shit. They're just talking religion. Is as soon as they told me this stupid photon theory. Photon is where I first said, oh, physics is, yeah, fuck it, they jumped the shark already. This stupid bullshit wave thing. They couldn't show me anything doing any of that crap. How exactly does the photon do all of this shit? How does it make sense to you? I mean, I don't know how you build this structure so that the tiny universe is so much more complex than our universe, right? The big universe is a lie because, oh no, the complexity is in this little universe. That's where all the interesting fields are and all the interesting bullshit. All the strings are tied to everything, all the millions of ropes. I mean, you might as well believe in a rope theory. What the fuck is you're talking about? It's moving in a field. A field of what? Shit. It's just spooky action. You got nothing. There's no physics to your physics. Alright. So, I don't know. It might be time just to block just another YouTuber. This is just useless. What does Jordan Peterson mean by clean up your room? I guess he would tell Einstein to comb his hair. I guess he means do everything while you're a dumbass. I don't know. I mean, clearly he's making some kind of argument that if you can't feed yourself, then you can't feed the world. But clearly cleaning your room is kind of a silly analogy because only an asshole could think that shit would be important, right? I mean, who's, really, who but silly women are going to waste their intellectual life running around with vacuum cleaners worried about every dust speck? I mean, so clearly it's irrelevant bullshit. I mean, it's good that Einstein didn't comb his hair. It's good that Einstein didn't give a fuck about, my flies unzipped. It's good that he didn't give a shit, okay? And so, yeah, it's just a silly notion that somehow people, he's almost like telling people in wheelchairs, learn how to walk before you get a job, or something like that. Like somehow we shouldn't recognize that, yes, some people have infirmities and disabilities, and but they can still be an active participant in the world because they don't have to walk everywhere. I mean, it's just a cruel, petty whine from a man who's probably his mother wiped his ass for him. I mean, he has every smell of a little only child mama's boy who's probably never made his own sandwich in his life. He's never had to clean his own room because he always had mommy to do it for him. So that's the problem with him. But fuck off with this bullshit. So one more stupid comment by you and you're done here. Not on any of these subjects. So fuck you. Anyway, so anything else? I don't think we need to bother with anything else. That's enough of videos. Those are good comments, but at least they have some specificity, they're relevant on the general subjects that have been brought up, and so that's positive. But I really need to. I need a physicist to argue with. I need a physicist to argue with. They have to answer some of my questions. This is just so unfair. I don't get to, I don't get to interrogate them on the depth of their knowledge and understanding. So anyway, until the next time. It's like the D. Hilster guy. I mean, they don't accept any critiques. They don't have any interest in defending their mush. They just spout bullshit that's just inaccurate. It's just so annoying. And they get away with it because they run from the argument. Alright, yeah, really, it's enough. Okay, so till the next time and such.